100 million years ago, you wouldn't recognize Earth. Stand anywhere on the planet and the world is alien. Continents are splitting apart in real time. Oceans flood lowlands, creating shallow seas where modern deserts now bake. The atmosphere? 30% richer in oxygen than what you're breathing right now. Carbon dioxide levels 4 times higher than pre-industrial. Global temperatures 10 degrees Celsius, warmer with no polar ice caps. Not a trace of ice anywhere on the planet. And dinosaurs. Not struggling survivors clinging to existence. Not relics of a fading dynasty. Apex architects of ecosystems, dominating every terrestrial niche, ruling continents for 80 million years at their absolute peak. But here's what you need to understand. This isn't the Jurassic. That was 50 million years earlier. Tyrannosaurus rex hasn't evolved yet. Triceratops doesn't exist. The Cretaceous period was ruled by different titans. Spinosaurus, Argentinosaurus, the largest land animal that ever walked the earth. Giganotosaurus. And something else was happening. Something revolutionary. Flowering plants, angiosperms, exploding in diversity, transforming landscapes from endless fern prairies to forests we might almost recognize. Pterosaurs with 10-meter wingspans soaring overhead. Mosasaurs 15 meters long, ruling the oceans like aquatic tyrannosaurs. The twist? This wasn't dinosaur decline. This was their golden age. Peak diversity, peak size, peak ecological dominance. The Cretaceous lasted 80 million years. That's longer than the entire age of mammals that followed. Longer than the time between the asteroid impact and right now. For 80 million years, this was dinosaur Earth. And then, 66 million years ago, in a single day, it ended. What was our planet like during dinosaur supremacy? How did climate, continents, and ecosystems create conditions for the largest land animals that ever existed? And here's the question that should haunt you. If that asteroid hadn't hit, would dinosaurs still be running things? Would you exist at all? The Cretaceous shows us an alternative evolutionary path. A world where reptiles, not mammals, became the planet's architects. Let's go back to the age when Earth belonged to giants. If you're fascinated by deep time and alternative Earth histories, please consider subscribing. This kind of long-form exploration takes time to research and create, and your support makes it possible. Thank you. Picture Earth from space 100 million years ago. You'd notice something immediately. More blue, less green. The planet is a water world compared to today. Sea levels are over 200 meters higher than modern. That's a 60-story building's worth of water above current coastlines. Why? No ice. None. Antarctica isn't a frozen wasteland. It's forested. Arctic Ocean isn't choked with pack ice. It's warm enough for crocodilians to paddle around near the North Pole. All that water that's currently locked up in ice sheets, it's in the oceans, and the continents are drowning. 18% of modern land area is underwater. Florida, gone. Most of Europe, an archipelago of islands. A shallow sea cuts North America in half from north to south. The western interior seaway, from the Arctic Ocean to the Gulf of Mexico. If you're in Kansas, you're underwater. If you're in Colorado, you're on the western shore looking east across hundreds of kilometers of shallow tropical sea. The Great Plains are a seabed, and this isn't temporary flooding. This is stable geography. For tens of millions of years, North America is two separate land masses. Laramidia to the west, Appalachia to the east. Never the twain shall meet. But the continents themselves are doing something dramatic. They're moving fast. Well, fast in geological terms. About as fast as your fingernails grow. Doesn't sound like much until you multiply it by 100 million years. Then you've moved continents thousands of kilometers. The supercontinent Pangaea, which existed 250 million years ago, is long gone. It started breaking up in the Jurassic. But the Cretaceous is when the fragments really scatter. South America and Africa are pulling apart. The South Atlantic Ocean is opening, seafloor spreading, magma welling up along the mid-Atlantic ridge. The continents are maybe halfway to their modern separation. You could still see across the ocean on a clear day, just barely. But give it another 70 million years and there'll be an ocean apart. The interesting thing is what this does to evolution. South America becomes an isolated island continent. Its dinosaurs evolve in complete isolation. Africa's fauna develops separately. And when we look at fossils, we can see the divergence. Different predators, different herbivores, same ecological roles, but filled by different lineages. North America and Europe are still connected, just barely. A land bridge across what will become the North Atlantic. But it's tenuous, intermittent, sometimes above water, sometimes below, depending on sea level fluctuations. Animals can cross, sometimes. Genes flow between continents until the connection finally breaks. And then the faunas diverge. Europe becomes an archipelago, islands. And on islands, something interesting happens. Animals shrink, island dwarfism. When you're stuck on a small island with limited resources, being giant is a liability. Smaller body size is favored. In Europe, we find dwarf sauropods, 6 meters long instead of 30, dwarf hadrosaurs. The same species that are 10 meters long on mainland Asia are 5 meters long in Europe. Evolution optimizing for island life. India is doing something particularly strange. It's a continent adrift. It broke off from Africa and Madagascar tens of millions of years earlier, and now it's sailing north across the Tethys Ocean, a lone subcontinent, moving at, geologically speaking, breakneck speed, several centimeters per year, racing toward Asia. It won't collide for another 30 or 40 million years. When it does, it'll crunch into Asia and crumple the crust upward into the Himalayas. But during the Cretaceous, it's alone, an arc of Gondwanan fauna floating north. And as it drifts, massive volcanic eruptions are building the Deccan Traps, flood basalts, lava flows that will eventually cover an area larger than France. That volcanism is already starting in the late Cretaceous. Some researchers think it contributed to the end Cretaceous extinction. But that's getting ahead of the story. Australia and Antarctica are still connected, forming the eastern edge of Gondwana. They'll separate in the Cenozoic, but for now, they're a single landmass. And it's not frozen. Far from it. Antarctica is covered in temperate forests, southern beech trees, conifers, ferns, and dinosaurs. Cryolophosaurus from the early Jurassic was just the beginning. We have fragmentary late Cretaceous fossils from Antarctica, hadrosaurs, ankylosaurs, an entire ecosystem we barely understand because it's now buried under 2 kilometers of ice. But it was there. Dinosaurs at the South Pole, living in forests, dealing with months of winter darkness, yes, but not cold. Not by modern standards, maybe freezing temperatures occasionally, but nothing like today. The ocean itself is different, warmer, much warmer. Sea surface temperatures in the tropics are around 35 degrees Celsius. That's 95 Fahrenheit. Hot tub temperatures. Permanently. The poles are around 15 degrees Celsius, 59 Fahrenheit. Cool by tropical standards, but astonishingly warm for polar regions. Today, polar oceans are around -2 to +2 Celsius. The difference is ice. When you have polar ice caps, they reflect sunlight. Albedo. The ice keeps itself cold. It's a self-reinforcing system. But without ice, the poles absorb solar heat, warm up, and stay warm. This creates a problem. Well, not a problem for the Cretaceous, but a difference. Today, our ocean circulation is driven by thermohaline circulation. Cold, salty water at the poles sinks and flows along the ocean bottom toward the equator. Warm surface water flows toward the poles to replace it. This is the global conveyor belt. It redistributes heat, moderates climate, but it requires cold water at the poles, dense water. In the Cretaceous, with warm poles, you don't have that. The temperature gradient from equator to pole is much smaller, maybe 15 degrees instead of 35. So ocean circulation is driven more by wind than by temperature and salinity differences. The oceans still circulate, but differently, sluggishly in the deep, vigorously at the surface, and the deep ocean is warmer. No cold bottom water. This has consequences. Oxygen levels in the deep ocean can drop, leading to anoxic events, times when the deep ocean loses its oxygen and becomes a dead zone. We see evidence of these in black shale deposits, organic rich sediments laid down in oxygen-poor water. But that's episodic. Most of the time, the Cretaceous ocean is healthy, thriving, full of life. The atmosphere. Let's talk about the air. You step out into the Cretaceous, take a breath, and it feels different, richer. Oxygen concentration is debated, but most estimates put it around 30%, compared to 21% today. That's a significant difference. Why does it matter? Oxygen diffusion. How easily oxygen moves from your lungs into your bloodstream, and from your blood into your cells. Higher oxygen concentration means easier breathing, more efficient respiration. For you, it'd feel like you're at sea level when you're actually at high altitude. Or like you're at high altitude getting sea level oxygen. You could run faster, longer, your cells would be happier. And for insects, it's even more dramatic. Insect respiration is passive. They don't have lungs, they have spiracles and tracheae, tubes that let air diffuse directly to their tissues. The efficiency of this system depends on oxygen concentration. Higher oxygen means insects can be larger. And in the Cretaceous, we do find large insects. Not Carboniferous giant dragonfly large, but bigger than modern. The oxygen is there to support them. But there's another gas we need to talk about. Carbon dioxide, CO2. Today, we're at around 420 parts per million. Before the Industrial Revolution, it was 280. In the Cretaceous, it's somewhere between 1,000 and 2,000 parts per million, 4 to 7 times pre-industrial levels. Now, before you panic, remember, this is natural. This is from volcanic outgassing. The Earth has a carbon cycle. Volcanoes release CO2. Weathering of rocks pulls it back out and deposits it as carbonates in the ocean. The balance between these processes determines atmospheric CO2. In the Cretaceous, volcanic activity is high. You've got mid-ocean ridges spreading fast. You've got large igneous provinces, flood basalts, the Caribbean, Ontong Java Plateau in the Pacific. These are dumping gigatons of CO2 into the atmosphere. And the weathering rate, while also high, isn't enough to keep up. so CO2 accumulates. What does high CO2 do? Greenhouse effect. Carbon dioxide is transparent to visible light, but absorbs infrared. Sunlight comes in, warms the surface, and the surface radiates heat as infrared. CO2 traps that heat, makes the planet warmer. Today, we're worried about going from 280 to 420 parts per million. That's enough to raise temperatures 1 degree Celsius and cause measurable climate change. In the Cretaceous, you're at 1,000 to 2,000 parts per million. The greenhouse effect is massive. That's why there's no ice. That's why the poles are 15 degrees instead of -40. That's why sea levels are so high. Thermal expansion of seawater plus meltwater from any ice that might have briefly existed. The Cretaceous is a hothouse, a greenhouse Earth, and it's stable. This isn't a temporary spike. This is tens of millions of years of hot, humid, high CO2 climate. Now you might think, hot planet, miserable conditions. But that's a modern human perspective. For dinosaurs, this is paradise. Ectotherms, cold-blooded animals, love warmth. It boosts their metabolism, makes them more active. Even if dinosaurs are mesotherms or partial endotherms, as much evidence suggests, warmth is beneficial. Less energy wasted on thermoregulation, more energy for growth, reproduction, activity, and the plant growth. With high CO2, plants photosynthesize more efficiently. It's like fertilizer in the air. Carbon is a limiting nutrient for plants. More carbon means more growth, lusher vegetation, more food for herbivores, which supports more herbivores, which supports more carnivores. The whole ecosystem is turbocharged. Precipitation patterns are different too. The hydrological cycle is more intense. Warmer atmosphere holds more water vapor, more evaporation from the oceans, more rainfall. The tropics get drenched. Seasonal monsoons are extreme. Rivers are enormous. Deltas sprawl across hundreds of kilometers. Swamps are extensive. The Hell Creek Formation in Montana and the Dakotas, which we'll talk about later, is a coastal plain. Rivers, floodplains, backwater swamps, constantly wet, constantly lush. Even at 45 degrees north latitude, where by modern standards you'd expect temperate or even boreal forest, it's subtropical, warm, humid, year-round growth. Deserts exist, but they're smaller and less common than today. The great desert belts of today are partly due to atmospheric circulation patterns and partly due to continental positions. In the Cretaceous, the continents are arranged differently. The circulation is different. There are arid zones, yes, but less extensive. Interior Australia might be dry, parts of Central Asia, but nothing like the Sahara or the Arabian Desert today. Most of the Cretaceous world is wet, green, alive. Seasonality is reduced. Today, the poles have 6 months of daylight and 6 months of darkness. The Cretaceous is the same in that regard. Axial tilt hasn't changed, but the darkness doesn't mean killing cold. It means cooler temperatures, maybe down to freezing briefly, but not sustained cold, not ice. Trees go dormant, animals hunker down, but they survive. Polar dinosaurs deal with the darkness by migrating, hibernating, or toughing it out. We find evidence of all three strategies. Bone beds showing mass migrations, growth lines in bones showing seasonal pauses in growth, like tree rings, suggesting dormancy or reduced food intake during winter, and simple presence of fossils showing some species just stayed put and dealt with it. The equator is hot but not uninhabitable, 35 degrees Celsius average. That's warm, but remember, It's humid. High CO2 atmosphere, lush vegetation, water everywhere. Animals can thermoregulate, stay in shade, wade in water, and many dinosaurs are large. Large body size is actually an advantage in stable, warm climates. It gives you thermal inertia. Your body temperature stays stable despite environmental fluctuations. You heat up slowly, cool down slowly. This is gigantothermy. Elephants use it today. Sauropods perfected it in the Mesozoic. When the environment is consistently warm, you don't need active thermoregulation. Your mass does the work. By 100 million years ago, the planet has been in hothouse mode for tens of millions of years. This isn't new. The dinosaurs have had time to adapt, to specialize, to diversify, and they have. By the late Cretaceous, dinosaur diversity is at its peak. More genera, more species, more ecological niches filled than at any previous point in their history. The Jurassic was impressive, but the Cretaceous is the culmination. 80 million years of uninterrupted dominance. Let's look at why. Something happened in the Cretaceous that changed everything. A botanical revolution. For most of dinosaur history, the world was green. Yes, but it was a specific kind of green. Ferns, cycads, ginkgos, conifers, gymnosperms, seed plants without flowers or enclosed seeds. These dominated the Triassic and Jurassic, and they continued into the Cretaceous. But around 130 to 125 million years ago, something new appeared. Small weedy plants with a strange reproductive strategy. Flowers, angiosperms, flowering plants. At first, they were insignificant. Marginal habitats, disturbed ground, riverbanks. Nobody paid attention, but they had a trick: fast reproduction. Gymnosperms take years to go from seed to reproductive maturity. Angiosperms can do it in months, weeks for some species. They reproduce quickly, disperse widely, adapt rapidly, and they co-evolved with insects. Pollination. Bees evolved around 130 million years ago, right as angiosperms were diversifying. Coincidence? No. Mutualism. The plants offer nectar and pollen. The insects provide pollination services. It's more efficient than wind pollination, more targeted, and it allows the plants to reproduce even when they're sparse. You don't need to be right next to another individual. Just need a bee to visit you and another plant. Gene flow increases. Evolution accelerates. By the mid-Cretaceous, around 100 million years ago, angiosperms are exploding in diversity. And by the late Cretaceous, 80 to 66 million years ago, they dominate the lowlands. Ferns still exist. Conifers still thrive in uplands and cooler regions. But the floodplains, the river valleys, the coasts, angiosperms, flowering trees, flowering shrubs, grasses are just evolving around 70 million years ago, but they're not dominant yet. That comes later in the Cenozoic. But the stage is set. The world is becoming modern in its botanical composition. Why does this matter for dinosaurs? Food. Angiosperms offer things gymnosperms don't. Fruits. Fleshy, nutritious structures designed to attract animals for seed dispersal. Flowers. High in protein and nutrients. Diverse leaf chemistry. Different defensive compounds. New feeding strategies are possible. Hadrosaurs, the duck-billed dinosaurs, have dental batteries. Hundreds of teeth packed together, constantly replacing, forming grinding surfaces. They can process tough, fibrous plant material. Angiosperms give them more options, more variety, more nutrition. Ceratopsians have shearing beaks and batteries of teeth too. They can slice through stems and leaves that would be difficult for other herbivores. The plant diversity drives herbivore diversity. More kinds of plants mean more ways to eat plants. More herbivore niches, more herbivore species, and herbivore diversity drives carnivore diversity. More prey species means more opportunities for predators. Different sizes of prey support different sizes of predators. Small theropods hunt small herbivores. Large theropods hunt large herbivores. Pack hunters take on prey larger than themselves. Solitary hunters specialize. The ecosystem becomes more complex. More niches, more species, more interactions. The Cretaceous food web is the most complex the Mesozoic ever produced. Let's talk about the dinosaurs themselves. The late Cretaceous, from 100 to 66 million years ago, is peak dinosaur. The greatest diversity, the largest sizes, the most specialized forms. Start with the herbivores, sauropods, the long-necked giants. In the Jurassic, they were everywhere. Diplodocids, brachiosaurids, camarasaurids. In the Cretaceous, one group dominates, titanosaurs, and they get big, really big. Argentinosaurus, found in Argentina as the name suggests. Estimated length, 30 to 35 meters. Weight, 60 to 100 tons. That's heavier than a Boeing 737. It's the largest land animal we know of, not the longest. Supersaurus and Diplodocus might have been longer, but the heaviest, the most massive. Why so big? Several reasons. High metabolism. Sauropods are now thought to have had elevated metabolic rates, not mammal level, but higher than typical reptiles. This requires lots of food. Being huge lets you eat vast amounts of low-quality forage. You're not picky. You eat everything within reach. Ferns, cycads, angiosperm leaves, whatever. Quantity over quality. Your gut is a fermentation vat. Microbes break down cellulose. You extract energy slowly but continuously, like a living compost heap. High browsing. Being tall lets you access food other herbivores can't reach. Sauropods can rear up on their hind legs, stretch their necks, reach into tree canopies. This reduces competition. You're not fighting for the same food as ground-level browsers. Predation defense. Once you're above a certain size, you're almost immune to predation. What's going to take down a 70-ton titanosaur? A pack of abelisaurids might try for a juvenile, but an adult? Forget it. You'd need a ridiculously large carnivore. And even the biggest theropods top out at 8 to 9 tons. That's 1/8 the mass of an adult titanosaur. Not happening. So titanosaurs evolve toward gigantism, and the only limit is biomechanics. How much weight can bones support? How much food can you gather? In the Cretaceous, with lush vegetation everywhere, the food limit is high. And sauropod skeletons are marvels of engineering. Hollow bones, air sacs extending from the lungs into the bones. This reduces weight. A titanosaur skeleton is maybe only 5% of body mass. Compared to mammals, where it's around 10%, they're half as skeletally expensive, which allows larger size. But sauropods aren't alone. Hadrosaurs are thriving. Duck-billed dinosaurs, Edmontosaurus, Parasaurolophus, Corythosaurus, Lambeosaurus, dozens of genera. They're everywhere. In North America, they're the most common large herbivores. More fossils of hadrosaurs than any other dinosaur group in Hell Creek Formation. Why so successful? Versatility. Hadrosaurs can walk on 2 legs or 4, bipedal when moving fast, quadrupedal when feeding. Their jaws are packed with teeth. dental batteries. Each battery has hundreds of teeth in vertical stacks. As the top teeth wear down, new ones erupt from below, constantly self-sharpening. They can grind through tough plant material, stems, leaves, even wood in some cases. And they're social. Bone beds show mass deaths, herds, possibly migrations. Trackways show groups moving together. There's safety in numbers. Predators have a harder time picking off individuals from a herd. And some hadrosaurs have elaborate crests, hollow bony structures on their heads. Parasaurolophus has a long, backward-pointing crest. Corythosaurus has a helmet-like crest. These are resonating chambers. Air passages inside the crest amplify sounds. Low-frequency calls, bellows, used for communication, recognizing species and individuals, attracting mates, coordinating herd movements. The Cretaceous was a noisy place. Ceratopsians, the horned dinosaurs. Triceratops is the icon. 3 horns, massive frill. But Triceratops only appears in the last 2 million years of the Cretaceous. Before that, other ceratopsians. Protoceratops in Asia, smaller. No horns, just a frill. Centrosaurus in North America. 1 nasal horn, Styracosaurus. Multiple spikes on the frill. Pentaceratops. 5 horns if you count the cheek spikes. These animals are built like living tanks. Massive heads, beaks for cropping vegetation, batteries of shearing teeth in the back of the jaws. They can slice through tough stems, palms, cycad fronds, angiosperm branches. The frill serves multiple purposes: display, species recognition, thermoregulation, maybe defense, though it's mostly just thin bone. Not much protection. The real weapons are the horns. Triceratops has 2 brow horns a meter long, sharp, forward-pointing. These are for fighting, males jousting over mates, or for defense against predators. A charging Triceratops is not something you want to face. 8 tons of angry herbivore with spears on its face. Ankylosaurs, the armored dinosaurs. Ankylosaurus, Euoplocephalus, low-slung, built like World War I tanks, covered head to toe in bony armor, osteoderms, bony plates embedded in the skin, spikes, ridges. The skull is fused into a solid mass. Only openings are for the eyes, nostrils, and ears. Even the eyelids have bone in them. And the tail. The tail ends in a club, a massive lump of fused bone. Swing that at a predator's leg, and you'll shatter bones, break knees. Ankylosaurs are herbivores, low browsers, eating ground-level vegetation, ferns, low shrubs, maybe roots. They don't move fast, don't need to. Nothing's going to eat them. Their armor is impenetrable. A tyrannosaur trying to bite an ankylosaur is risking broken teeth. Not worth it. So ankylosaurs just waddle around, munching plants, secure in their mobile fortresses. Pachycephalosaurs, the bone-headed dinosaurs. Pachycephalosaurus, Stygimoloch, Dracorex. Actually, those last 2 might just be juveniles of Pachycephalosaurus. The taxonomy is messy, but the defining feature is the skull. Domed, thickened, solid bone up to 25 centimeters thick. What's it for? Headbutting, males ramming each other, competing for mates, like modern bighorn sheep. The idea has been debated. Some researchers think the dome is too fragile, would crack under impact. But biomechanical modeling suggests it could work. And we find pathologies in some skulls, healed fractures, consistent with impact. So probably, yes, they were butting heads. Seems insane. But so does a giraffe swinging its neck to club another giraffe in the head, and they do that. Evolution finds ways. Now the predators, theropods. This is where it gets interesting. Tyrannosaurids are the most famous. Tyrannosaurus rex, the king. 8 to 9 tons, 13 meters long, 2 meters tall at the hip, 5.5 meters tall when standing upright, which it rarely did. The skull alone is 1.5 meters long, 60 teeth, each tooth up to 30 centimeters long, including the root. Serrated, banana-shaped, not blade-like like most theropods. These are crushers. Bite force estimated at 57,000 newtons, 12,000 pounds force. The strongest bite of any land animal. Stronger than a saltwater crocodile. Stronger than a great white shark. Strong enough to bite through bone. And we know T-Rex did that. We find bite marks on prey bones. Hadrosaur vertebrae with T. Rex tooth marks. Triceratops frills with punctures. And most tellingly, coprolites, fossilized feces, from T-Rex, containing bone fragments, big pieces, crushed bone. T-Rex was eating bone, either scavenging and consuming entire carcasses or actively crushing bones to access marrow. Probably both. Was T-Rex a hunter or a scavenger? The debate raged for years. Current consensus, both. Opportunistic. It would hunt when it could, scavenge when it could. Like most large carnivores today, lions hunt, but they also steal kills and scavenge. Hyenas hunt, but they scavenge. T-Rex had excellent vision, forward-facing eyes, binocular vision, depth perception. That's a hunter's trait. And the sense of smell. Olfactory bulbs in the brain are huge. It could smell a carcass from kilometers away. Scavenger's trait. So it did both. Practical. But T-Rex is late Cretaceous. Last 3 million years before the extinction. Earlier in the Cretaceous, other tyrannosauroids, Albertosaurus, Daspletosaurus, Gorgosaurus, smaller, 5 to 6 tons, still formidable. And before them, in the mid-Cretaceous, tyrannosaurs are small, human-sized, not the apex predators yet. That niche is filled by others, Carcharodontosaurids, shark-toothed dinosaurs, named for their teeth, blade-like, serrated, like a great white shark. Giganotosaurus in South America, 12 to 13 meters long, 8 tons, possibly larger than T-Rex, competing for the title of largest land predator. Carcharodontosaurus in North Africa, similar size. Mapusaurus in Argentina. These are the apex predators of Gondwana in the mid-Cretaceous. They hunt sauropods, pack hunting possibly. A bone bed in Argentina shows multiple Mapusaurus individuals together. Maybe they died in a drought, or maybe they were hunting together. Coordinated attacks on titanosaurs, slash and bleed. Bite force isn't as strong as T-Rex, can't crush bone, but the teeth are sharp, slice through flesh, cause massive bleeding. Hit and run tactics. Attack, retreat, let the prey weaken, then finish it. Spinosaurids. Now here's where it gets weird. Spinosaurus, 15 meters long, possibly 7 to 8 tons, but built nothing like other theropods. Long, narrow jaws, conical teeth, not serrated, not for slicing flesh, for gripping, like a crocodile. And the body, elongated. Neural spines on the back vertebrae extend upward, up to 1.7 meters tall, forming a sail or hump. What's it for? Display? Thermoregulation? No one's sure. But the real revelation came in 2020, a nearly complete Spinosaurus skeleton, and it's aquatic, dense bones. In most theropods, bones are hollow, air-filled. Lightweight, Spinosaurus bones are solid, heavy, like penguin bones. They reduce buoyancy, help you dive. And the tail is tall, paddle-shaped, with elongated neural spines and chevrons forming a deep fin. This is a swimming tail. Crocodilian. Spinosaurus swam, hunted fish, We find it associated with aquatic deposits, river channels, coastal lagoons. It's a semi-aquatic theropod, the only one we know of, which makes sense. Different niche, no competition with land-based predators. Fish are abundant. Large coelacanths, sawfish 2 meters long. Spinosaurus waddles into the water, swims, snaps up fish with those crocodile jaws. It's bizarre, but effective. Evolution fills every niche. Abelisaurids in the southern hemisphere, South America, Africa, India, Madagascar. Carnotaurus is the most famous, 7 to 8 meters long, 1 to 2 tons. Horns over the eyes, tiny vestigial arms, even smaller than T-Rex arms. Basically, useless. Why? No one knows. Maybe sexual selection. Maybe they're just not needed. Abelisaurids have strong legs, strong jaws. That's enough. The arms are baggage, evolutionary leftovers. But Carnotaurus is fast. Estimates suggest it could run at 50 kilometers per hour, 30 miles per hour for a brief sprint. That's faster than most hadrosaurs. Fast enough to run down prey or escape larger predators, if there were any. In South America, abelisaurids are the top predators. Carnotaurus hunts sauropods, probably juveniles. An adult titanosaur is too big, but a 5-ton juvenile? Feasible, especially in a pack. Dromaeosaurids, the raptors, Velociraptor, Deinonychus, Utah raptor. These are the intelligent hunters, small to medium-sized. Velociraptor is only 2 meters long, 15 kilograms, turkey-sized, not the human height monsters from the movies. Deinonychus is larger, 3.4 meters, 70 kilograms, about the size of a large dog. Utahraptor is the giant, 7 meters, half a ton. But all of them share the key feature, the sickle claw. On the second toe of each foot, a huge, curved, retractable claw, held off the ground when walking, deployed when attacking. Used for gripping, climbing onto prey, slashing, maybe disemboweling. The debate continues, but it's a weapon. Dromaeosaurs hunt in packs, probably. A Deinonychus bone bed in Montana shows multiple individuals with a Tenontosaurus herbivore. They died together. Flash flood, maybe. But they were together. Hunting, scavenging, either way, cooperative. And they're smart. For dinosaurs, brain-to-body mass ratio is relatively high. Troodon is even higher. Encephalization quotient around 0.4. Compared to modern birds, which range from 0.5 to 2. Mammals from 0.5 to 7. Humans are around 7. So Troodon and dromaeosaurs are in the lower range of bird intelligence, which means they're clever, problem-solving, learning, social coordination, not building tools, but capable of complex behavior. Feathers. We need to talk about feathers, because by the Cretaceous, it's clear that many theropods had them. Not just small ones, not just the ancestors of birds, proper dinosaurs. Yutyrannus, a tyrannosaur relative from China, 9 meters long, 1.4 tons, covered in filamentous feathers, long, shaggy protofeathers, found preserved in lake deposits. The whole body. This is not a small animal. This is a large predator, and it's fuzzy. Why? Insulation, probably. Yutyrannus lived in cooler climates, northern China during the early Cretaceous. Temperatures were lower than equatorial regions. Feathers helped retain body heat, especially if it had an elevated metabolic rate, which the evidence increasingly suggests. Smaller theropods were definitely feathered. Microraptor, 4-winged. Feathers on the arms and legs, iridescent. We know this because fossilized melanosomes, the pigment structures in feathers, preserve. Under electron microscopy, you can identify the type of melanosome, and from that, infer color. Microraptor was black with iridescent blue and green sheens, like a crow or a grackle. Sinosauropteryx, one of the first feathered dinosaurs discovered, had a striped tail, reddish brown and white bands, counter shading on the body, dark on top, light on the belly. This is camouflage, reduces the appearance of three-dimensional form, makes you harder to see. Modern animals use it. Deer, fish, birds. Sinosauropteryx was using it 125 million years ago. Psittacosaurus, a small ceratopsian, had quills, long hollow structures on its tail. Not feathers, something else. Unique to this lineage, as far as we know. Display structures, maybe sensory. The preservation in some specimens is exquisite. You can see the individual quills, counter shading on the body, dark back, light belly, again camouflage. And these are juveniles, small, vulnerable. They needed to avoid predators. Camouflage helped. But what about the big ones? Did T-Rex have feathers? Contentious question. We have skin impressions from T-Rex, scales, pebbly skin, no feathers. But the skin impressions are from small patches. Tail, hip, neck, not the whole body. It's possible T-Rex had feathers on parts of the body and scales on others, especially when young. Juveniles might have been feathered for insulation. Adults might have lost most feathers due to size. Large animals have low surface area to volume ratios. They retain heat easily. Too much insulation causes overheating. Elephants lose their hair as adults. Maybe T-Rex did the same with feathers. Or maybe it never had them. Its ancestors did. Yutyrannus did. But T-Rex lived in warmer climates. Late Cretaceous Hell Creek was subtropical. Maybe feathers were unnecessary. Lost. We don't know. The debate continues, but it's clear that feathers were widespread among theropods. Not universal, but common. Flight. Birds evolved from small theropods in the Jurassic. By the Cretaceous, birds are diversifying. True birds. Aviale. Hesperornis is a flightless diving bird, 1.5 meters long. Legs positioned far back on the body, like a loon or grebe. It swam. Dove for fish. Lived in the western interior seaway. Wings reduced to tiny vestiges, useless for flight. But it had teeth, rows of small teeth in the jaws, used for gripping slippery prey. Most modern birds are toothless, but Cretaceous birds retained teeth. Ichthyornis, a tern-like bird, also had teeth. It flew, fished, coastal environments. By the end of the Cretaceous, there are thousands of bird species, maybe 10,000, diverse, occupying ecological niches, small insectivores, fish eaters, maybe some scavengers, but none are large. All are small, under a few kilograms. The large flying niches are occupied by something else. Pterosaurs. Pterosaurs, not dinosaurs, a separate lineage, but they dominated the skies for the entire Mesozoic. And in the Cretaceous, they reached their peak, size-wise, diversity-wise. Pteranodon is the classic, wingspan 7 meters, toothless beak, huge crest on the back of the head. Males have larger crests than females. Sexual dimorphism. Display structure. Pteranodon flew over the western interior seaway. Soared. Dipped to the surface to snatch fish. Like a giant albatross. But unlike birds, pterosaurs have membranous wings. Skins stretched between an elongated fourth finger and the body. The other 3 fingers are small, clawed, used for climbing or gripping. When on the ground, pterosaurs walked quadrupedally, on all fours, awkward-looking but functional. But Pteranodon is not the largest, not even close. Quetzalcoatlus, named after the Aztec feathered serpent god. Wingspan 10 to 11 meters. That's a small airplane. 35 feet, the largest flying animal that ever lived. Mass estimates vary. 200 to 250 kilograms, about the weight of a large male lion. Standing on the ground, it's as tall as a giraffe, 5.5 meters. How did it fly? That's been debated. Some argued it couldn't. Too heavy. But biomechanical modeling shows it's possible. Barely. The wings are huge, lightweight. The bones are hollow, thin-walled. Air sacs throughout the body. Extremely low density. The wing membrane is thin but strong, reinforced with fibers, actinofibrils, like the rigging on a sailboat. And the flight muscles are massive. Pterosaurs had large sternums with keels for muscle attachment. They could launch themselves into the air with a quadrupedal leap, vault upward, start flapping. Once airborne, they'd soar. Thermals, rising columns of warm air, like modern vultures. Quetzalcoatlus probably didn't flap much. Soaring was more efficient, covered huge distances, hundreds of kilometers in a day. What did it eat? Carrion, possibly, scavenging like a vulture. But the beak is long and pointed, not hooked like a vulture, more like a stork or heron. Some researchers think it was a terrestrial stalker, walked on the ground, used its beak to probe for small animals, lizards, mammals, baby dinosaurs, stabbed them, swallowed them whole, like a marabou stalk. This is supported by trackways. Pterosaur footprints show they spent time on the ground, walking, foraging. So Quetzalcoatlus might have been more terrestrial than expected, flying between feeding sites, but hunting on foot. Bizarre, but effective. Other pterosaurs filled different niches. Ornithocheirus, fish eater, long jaws with interlocking teeth, crest on the snout, helped with hydrodynamics, skimming the water surface. Tupexuara, short, tall head with a massive crest. Display structure, possibly fed on fruit. Or carrion, Nyctosaurus, bizarre crest. Two long prongs extending upward and backward from the skull. Maybe supported a skin sail, used in display, or stabilization during flight. Pterosaur diversity is high in the Cretaceous. But by the late Cretaceous, diversity is declining. Extinction of some families. Competition with birds, perhaps. But the giants, the Ajdarchids like Quetzalcoatlus, persist until the end. They're there at the extinction event, and then they're gone, forever. Now, let's go into the water, the oceans, because the Cretaceous oceans are ruled by reptiles, marine reptiles, not dinosaurs. Different groups, mosasaurs, plesiosaurs, sea turtles, crocodilians. Mosasaurs are the apex predators. They're relatives of modern monitor lizards, varanids, but fully aquatic. They evolved in the mid-Cretaceous. By the late Cretaceous, they're everywhere. All oceans. Top predators. Tylosaurus, 15 meters long, 2 tons, maybe more. Long, streamlined body, powerful tail for propulsion, 4 flippers, modified limbs, not for walking, for steering. The jaws are long, filled with teeth, conical, recurved, for gripping. And here's the kicker. Mosasaurs have a second set of jaws, pterygoid teeth. In the roof of the mouth, when they bite down, the prey is impaled on the main teeth. Then the pterygoid teeth engage, pull the prey backward into the throat, like a snake. Mosasaurs are related to snakes. This double jaw system is a shared trait. It allows them to swallow large prey, whole fish, other marine reptiles, even smaller mosasaurs. Cannibalism is documented. Bite marks on mosasaur bones from other mosasaurs. What did they eat? Everything. Fish, ammonites. We find crushed ammonite shells with mosasaur bite marks. plesiosaurs, sea turtles, even sharks. A Tylosaurus stomach contents fossil shows remains of a shark, a bony fish, a smaller Mosasaurus, and a flightless diving bird. It was an indiscriminate predator, ate whatever it could catch, and it could catch a lot. Fast swimmer, ambush predator. Some species had binocular vision, forward-facing eyes, depth perception. Hunting in 3 dimensions in open water requires that. Mosasaurs were the ocean's tyrannosaurs, dominant, ubiquitous, successful. Plesiosaurs are still around, but declining. They were more diverse in the Jurassic. By the Cretaceous, 2 main types remain: long-necked plesiosaurs, Elasmosaurus. 14 meters long, but most of that is neck, 7-meter neck, tiny head. How did it use that neck? Fishing, darting the head sideways to snatch small fish. The neck is flexible, allows quick strikes, but it's not strong, can't handle large prey. So Elasmosaurus feeds on small fish, squid, maybe ammonites. It's a specialist, and specialists are vulnerable to environmental change. If their food source declines, they're in trouble. Short-necked plesiosaurs, pliosaurs. These are different. Short neck, massive head, huge jaws. Kronosaurus, 10 meters long, skull 2.5 meters. This is an apex predator, competed with mosasaurs. But pliosaurs are rarer in the late Cretaceous, less common. Maybe outcompeted by mosasaurs. Maybe environmental changes, sea level fluctuations, ocean chemistry. We don't know, but they're declining. Sea turtles, Archelon, 4.5 meters long, shell, but not a heavy domed shell like land turtles. A lighter, flatter shell, almost a skeleton of a shell. Reduced weight for swimming. Flippers, massive front flippers for propulsion, smaller rear flippers for steering. Archelons swam slowly, cruised the open ocean, fed on jellyfish, probably like modern leatherback turtles. Jellyfish are low in nutrition. You have to eat a lot. Archelon did, grew huge. And the shell? Defense. Even with a reduced shell, it's protection. Mosasaurs might have tried to bite it, but the shell is tough, keratinous, covering over bone, hard to crack, easier to find other prey. Crocodilians, not just in rivers, in the ocean. Deinosuchus, literally terrible crocodile, 10 to 12 meters long. Weight estimated at 3 to 5 tons. It lived in coastal environments, river mouths, estuaries, and it hunted dinosaurs. We have bite marks on the hadrosaur bones matching Deinosuchus' teeth. It ambushed herbivores coming to drink, grabbed them, pulled them into the water. Death roll. Crocodilians use a death roll to tear chunks off large prey. Spin rapidly along the body axis. The prey can't resist the rotational force. Limbs tear off. Body parts rip away. Deinosuchus was doing this to 8-ton hadrosaurs. In the water, the crocodile has the advantage. On land, the dinosaur could fight back. But in water, no chance. Ammonites, shelled cephalopods, relatives of modern nautilus. They're thriving in the Cretaceous. Thousands of species, all sizes, some tiny, some over 2 meters in diameter. The shell is coiled, chambered. Gas-filled chambers provide buoyancy. The animal lives in the outermost chamber, has tentacles, feeds on small prey, fish, plankton, and ammonites are prey for mosasaurs, turtles, fish. Their shells are tough, but crushable. We find ammonite shells with bite marks, holes, crushed sections. They're a major food source, and they're diverse. Different shell shapes, different ornamentations, ribs, spines, smooth shells, complex suture patterns where the internal chambers meet the shell wall. These patterns are unique to each species, used for identification. Ammonites are index fossils, used to date rock layers. Different species lived at different times. Find a certain ammonite, and you know the age of the rock, accurate to within a few 100,000 years. They're invaluable for stratigraphy. Bony fish are diversifying. Modern groups are appearing. Teleosts, advanced ray-finned fish. They have flexible jaws, can protrude their mouths, suction feeding, more efficient, better at grabbing prey. Teleosts replace earlier fish groups. By the Cretaceous, they're dominant. And sharks. Modern shark groups are evolving. Requiem sharks, hammerheads, great whites. Well, not yet, but their ancestors. Lamniforms, mackerel sharks. Fast, predatory. The Cretaceous ocean is recognizable. Modern. The players are mostly familiar. It's the reptiles that are alien. Let's pick a place. A snapshot. Hell Creek Formation. Montana, North Dakota, South Dakota, Wyoming. 68 to 66 million years ago. The last 2 million years before the asteroid. This is the most studied late Cretaceous ecosystem. Why? Because it's well preserved, and because it's the end, the final act. Hell Creek shows us what was there when the lights went out. Geography. Hell Creek is a coastal plain, low-lying, flat. The western interior seaway is retreating. Sea levels are dropping. The seaway, which bisected North America for millions of years, is pulling back. By Hell Creek time, it's mostly gone, reduced to a narrow arm in the north. But the landscape is still wet. Rivers, lots of rivers, meandering channels, oxbow lakes, backwater swamps, floodplains. The climate is warm, subtropical, mean annual temperature around 19 degrees Celsius, 66 Fahrenheit, seasonal, wet season and dry season, but never cold. Frost is rare, maybe a few nights a year. The vegetation is lush. Angiosperms dominate the lowlands. Flowering trees, shrubs, ferns in the understory, conifers on higher ground, palms, cycads. It's a mixed flora, transitioning from the older Mesozoic gymnosperms to the newer angiosperms. But the angiosperms are winning. The fauna, dinosaurs everywhere. T-Rex is the apex predator. An adult T-Rex in Hell Creek is about 8 tons, maybe 9 for the largest individuals, not the biggest theropod ever. Giganotosaurus and Spinosaurus might have been heavier, but T-Rex is the most powerful. The bite force, the bone-crushing jaws, it's optimized for killing large armored prey, which is good, because Hell Creek has a lot of armored herbivores. Triceratops is the most common large herbivore. For every T-Rex fossil, there are dozens of Triceratops. They're everywhere. Herds. Fossil bone beds show mass deaths, floods, droughts. Triceratops caught in bad situations. Adults are 8 to 9 tons, 3 meters tall at the shoulder, 7 to 9 meters long. The frill is 2 meters across. The brow horns are 1 meter long. Forward pointing, sharp. These animals are not defenseless. A T-Rex trying to take down an adult Triceratops is risking injury. Gored, trampled. It's dangerous. T-Rex probably targeted juveniles or sick adults. The weak, the unlucky, but Triceratops fights back. We have a Triceratops pelvis with a T-Rex bite mark. Healed. The animal survived, got bitten, escaped, lived. The bone healed around the wound. We also have a T-Rex tooth embedded in a Triceratops vertebra, and a Triceratops horn that shows evidence of repeated combat, scarring, remodeling. These animals fought each other, predators. Life in Hell Creek was violent. Edmontosaurus, hadrosaur, duckbill, second most common herbivore, 12 meters long, 4 tons, herds. We have bone beds with dozens of individuals, trackways showing groups moving together. Edmontosaurus had dental batteries, could grind tough vegetation, stems, leaves, bark, maybe even small branches. No defense mechanisms, no horns, no armor, just size and speed. A running hadrosaur could reach 30 kilometers per hour, 20 miles per hour, for a brief sprint, enough to escape a pursuing predator. Maybe, if you're not the slowest in the herd. Ankylosaurus, a tank, 6 to 8 meters long, 4 to 6 tons, covered in armor, osteoderms, bony plates, spikes on the sides. The tail club is massive, fused bone, weighs maybe 60 kilograms. Swing that, and it's a devastating weapon. Biomechanical modeling shows the club could generate enough force to break bone. A T-Rex femur is strong, but a full-force hit from an Ankylosaurus tail club could fracture it, cripple the predator. Ankylosaurus doesn't run, doesn't need to. It just stands there, lets the predator try. And if the predator gets too close, wham, broken leg. Predator starves. Ankylosaurus walks away. Pachycephalosaurus, the bonehead, 4 to 5 meters long, maybe half a ton, bipedal, fast. The skull dome is 25 centimeters thick, solid bone. Males had thicker domes than females, used in intraspecific combat, headbutting, dominance displays, mating rites. Pachycephalosaurus is less common than the big herbivores, but it's there, filling a niche. Mid-sized herbivore, eating low vegetation, ferns, shrubs, flowers. The Celosaurus, a small ornithischian, 3 to 4 meters long, maybe 300 kilograms, bipedal, fast runner, no armor, no weapons, just speed. And there are small theropods, dromaeosaurs, Acheroraptor, similar to Velociraptor, 2 meters long, probably hunted in packs, took down small prey. Pachycephalosaurus juveniles, mammals, lizards, birds, and maybe scavenged. Carcasses are a resource. Anything that dies gets scavenged. Tyrannosaurs, dromaeosaurs, crocodiles, scavengers all. Ornithomimus, ostrich mimic, 3 to 4 meters long, maybe 150 kilograms, bipedal, very fast, could run 50 kilometers per hour, 30 miles per hour, faster than any predator, omnivore, ate plants, small animals, eggs, insects, opportunistic. The beak is toothless, covered in keratin, like a bird, used for pecking, nipping, grabbing. Ornithomimus is common, quick, wary, hard to catch. Crocodilians, Brachychampsa, 2 to 3 meters long. Opportunistic predator, fish, turtles, small dinosaurs, scavenged carcasses, lived in rivers and swamps, and there were turtles, champsosaurs, long-snouted aquatic reptiles, not true crocodilians, a separate lineage, fed on fish, mammals, small, nocturnal, insectivores, omnivores. The largest is maybe 10 to 15 kilograms, about the size of a house cat. Most are smaller, rat-sized, shrew-sized. They're there, in the underbrush, in burrows, active at night when dinosaurs are less active, staying out of the way, surviving, waiting, but they're not important, not ecologically. They're marginal. The world belongs to dinosaurs, birds, dozens of species, small, fish eaters, insectivores, seed eaters, flying, hopping through the trees, calling. The soundscape of Hell Creek includes bird calls, chirping, whistling, but also dinosaur vocalizations, hadrosaurs bellowing, low-frequency calls resonating through the valleys, tyrannosaurs roaring, hissing. The audio environment is rich, layered, complex. Pterosaurs, Quetzalcoatlus is there, soaring high, circling, looking for carrion or live prey. On the ground, it walks, stalks, hunts, a giant stork, and smaller pterosaurs. But they're rare, declining. Birds are outcompeting them in many niches. Insects, everywhere. Beetles, flies, wasps, bees, ants are just evolving. Butterflies, moths, dragonflies, mosquitoes, ticks. The insects are mostly modern groups. You'd recognize them, and they're abundant, pollinating flowers, decomposing dead matter, being eaten by birds and small theropods. The insect diversity is high, thousands of species, supporting the entire ecosystem. Without insects, the angiosperm forests collapse. The pollination stops, the decomposition slows. Insects are the foundation. Plants. The forest structure is complex. Canopy trees, 30 to 40 meters tall, platanoids, relatives of modern sycamores, laurels, magnolias, understory trees and shrubs, ferns, ground cover, palms in wet areas, cycads, conifers on slopes. The plant diversity is high, dozens of tree species, hundreds of herbaceous species, and they're flowering seasonally. Flowers attract insects, insects pollinate, fruits develop, seeds disperse, animals eat the fruits, carry the seeds, defecate elsewhere, seeds germinate. The mutualism between plants and animals is sophisticated, co-evolved, tight. The rivers are full of fish, gar, bowfin, sturgeon, relatives of modern species, and freshwater sharks, hybidus, small, maybe a meter long, predatory. Crocodiles cruise the riverbanks, ambush predators, patient. Dinosaurs come to drink, young, unwary. The crocodile strikes, drags them under, drowns them, eats them. This is Hell Creek, a functioning ecosystem, stable, productive, complex. It's been like this, more or less, for millions of years. The species change, evolution continues, but the structure remains. Dinosaurs dominate, mammals hide, reptiles rule sea and sky. And then, 66 million years ago, an asteroid 10 kilometers across hits the Yucatan Peninsula at 20 kilometers per second. The energy release is 100 million megatons. The impact winter lasts years. Photosynthesis stops. Food chains collapse. 75% of species go extinct, including all non-avian dinosaurs. But we'll get to that later. For now, understand, Hell Creek was thriving. This wasn't a world in decline. This was dinosaur Earth at its peak, and it ended in a day. Let's look south. South America, Patagonia, the southern tip, 70 to 90 million years ago. This is Gondwana. The southern supercontinent is fragmenting. South America is pulling away from Africa. The South Atlantic is opening. But South America is still connected to Antarctica, and through Antarctica to Australia. A land bridge. Faunal exchange is possible, but South America is becoming isolated, an island continent. And on an island, evolution does strange things. The herbivores, titanosaurs, huge titanosaurs, Argentinosaurus, Patagotitan. These are the largest land animals ever, 35 to 40 meters long, 70 to 100 tons, compared to the largest African elephants, 6 tons. Argentinosaurus is 15 times heavier. How does an animal that large function? Walking is a challenge. The legs are columnar, straight, like pillars, supporting the weight. The feet are broad, spreading the load. The bones are massive, but also lightweight. Hollow, air sacs from the respiratory system invade the bones. Pneumatic bones. This reduces weight without sacrificing strength. The vertebrae are complex, interlocking processes, weight-saving holes and chambers, engineering marvels, natural selection optimizing for size, feeding. Argentinosaurus needs hundreds of kilograms of food per day. It's a browser, reaches into tree canopies, strips leaves, swallows them whole. No chewing. The teeth are simple, pegs, used for raking leaves off branches, not for grinding. The grinding happens in the gut. A massive fermentation chamber, gastroliths, stomach stones, swallowed rocks. In the gizzard, they mill the plant material, break it down mechanically, then microbes ferment the cellulose, extract nutrients. It's slow, inefficient, but it works. The gut is enormous, maybe taking up a third of the body volume. A walking fermentation vat. Reproduction. Argentinosaurus lays eggs, large eggs, maybe 30 centimeters in diameter, but not that large relative to the adult. A 100-ton animal laying a football-sized egg. The babies hatch small, maybe 10 kilograms, and then they grow, fast. Bone histology shows rapid growth rates, reaching adult size in maybe 20 to 30 years. Fast for a reptile, more like a mammal. This suggests high metabolic rates, warm-bloodedness, or at least mesothermy, intermediate metabolism. Not cold-blooded, not fully warm-blooded, somewhere in between. Efficient, allowing rapid growth without the extreme energy costs of full endothermy. The predators, not tyrannosaurs. South America doesn't have tyrannosaurs. It has abelisaurids, Carnotaurus, Abelisaurus, smaller, 5 to 8 meters long, 1 to 2 tons, but the top predators nonetheless. Carnotaurus has horns, brow horns, short, blunt, used in intraspecific combat, males fighting males, headbutting, wrestling. Display? The arms are tiny, vestigial, smaller than T-Rex arms, essentially useless, 4 fingers. But the hands are so reduced they can't grip, can't hold, can't do anything. Why retain them? Evolutionary baggage, or maybe some function we don't understand. Sexual display, who knows? Carnotaurus hunts. Probably. It's fast. Leg proportions suggest speed, maybe 50 kilometers per hour. 30 miles per hour. Chases down prey. Sauropods, not adults, but juveniles. A 5-ton juvenile titanosaur is feasible prey, or smaller ornithopods. Pack hunting is possible. No direct evidence. But modern large carnivores often hunt in groups. Lions, wolves, hyenas. It's more efficient. Brings down larger prey. Shares the risk. If abelisaurids hunted in packs, they could tackle larger sauropods. Wound them, bleed them, track them until they weaken. Then finish them. Other theropods, megaraptorids, long-clawed theropods, 8 meters long, fast, slashing claws on the hands, used to wound prey, raptor-like in behavior but not closely related. And smaller theropods, alvarezsaurids, tiny arms with one massive claw, used for digging. Termites, insectivores, specialized, filling niches, flying reptiles. Pterosaurs, large ones, Tropeognathus, wingspan 8 meters, crested snout, fish eater, soared over coastal waters. And inland pterosaurs, Thapungaka, massive skull, 7 meters wingspan, terrestrial stalker, probed for prey with the long beak. Patagonia is pterosaur territory. Birds, early forms, enantiornithines, toothed birds. Opposite birds, the name refers to the shoulder joint. Different structure from modern birds. Diverse, dozens of species. Small, insectivores, seed eaters, tree dwellers, but not yet dominant. Pterosaurs still hold the larger flying niches. Patagonia is hot, dry in the interior, wetter near coasts, seasonal rivers, floodplains. During the wet season, the rivers overflow, create vast wetlands. Dinosaurs congregate, nesting grounds. Titanosaurs lay eggs in colonial nests, like sea turtles. Dig shallow pits, lay dozens of eggs. Cover them, leave. No parental care. The eggs incubate in the warm ground. Heat from decomposing vegetation. Solar heat. Months later, they hatch. The babies are on their own. Many die. Predators. Starvation. But some survive. Grow. Join the herds. We have a site in Argentina, Auca Mahuevo. Thousands of titanosaur eggs, nesting ground used for generations, layer upon layer of eggs, some fossilized with embryos inside, preserved skin impressions, scales, no feathers. Sauropods are scaly. We can see the individual scales, tiny, pebbly, covering the body, and the eggs are in clutches, groups. Each female laid maybe 20 to 40 eggs per season. High reproductive output, necessary. Juvenile mortality is high. The environment is harsh. Dry season, water scarce, vegetation withers, herbivores migrate. Follow the rains, follow the green. Predators follow the herds. It's like the Serengeti. Migratory patterns, seasonal movements. Trackways show this. Parallel tracks. Groups moving together. Hundreds of individuals. Sauropod highways. Paths worn into the ground by repeated use. Patagonia is isolated, but not completely. Occasionally, animals cross from Antarctica, or Madagascar, or Africa early in the Cretaceous. Gene flow occurs, but it's limited. So South American fauna diverges, becomes unique. Abelisaurids instead of tyrannosaurs. Titanosaurs dominating more than in other continents. Unique bird lineages. By the end of the Cretaceous, South America is its own world. And when the extinction comes, it hits hard. The unique fauna, gone. Replaced, eventually, by immigrants from North America after the continents reconnect in the Cenozoic. But that's later. Now Africa, specifically North Africa, the Sahara. Today, it's the largest hot desert on Earth. Barren, lifeless, dunes, rock. But 100 million years ago, it's lush. Rivers, deltas, swamps, the Kem beds in Morocco. These deposits are coastal, river mouths, tidal zones, wet, productive, full of life, and dangerous. Spinosaurus. We talked about it earlier, but let's revisit. 15 meters long, 7 to 8 tons, semi-aquatic, dense bones, paddle tail, crocodile jaws, conical teeth. This is an animal that lives in and around water. It swims, dives, catches fish, large fish, coelacanths. Sawfish, lungfish. These fish are huge. The sawfish, Onchopristis, is 7 meters long, saw-like rostrum lined with teeth, used to slash prey or defend against predators. But Spinosaurus eats them anyway. The jaws are powerful, the teeth interlock. Grip, hold the fish, pull it in, swallow. Maybe tear chunks, but mostly whole. Spinosaurus isn't alone in the water. Sarcosuchus, a giant crocodilian, 12 meters long, 8 tons, larger than any modern crocodile. The skull alone is nearly 2 meters, jaws lined with over 100 teeth, conical, interlocking, built for gripping, not chewing. Sarcosuchus is an ambush predator, lies in wait, submerged, eyes and nostrils above water. A dinosaur comes to drink. The crocodile strikes, explodes from the water, jaws clamp onto the prey, drags it under, drowns it. Then the death roll, spinning, tearing limbs off, breaking bones. Sarcosuchus eats dinosaurs, fish, whatever comes near the water. It's not picky. And there's competition on land. Carcharodontosaurus, shark-toothed lizard, 12 to 13 meters long, 6 to 8 tons. The apex terrestrial predator of North Africa. Blade-like teeth, serrated. Each tooth is 20 centimeters long, designed to slice, cause massive blood loss. Carcharodontosaurus hunts sauropods, mid-sized sauropods, 10 to 15 tons. Rabachisaurus, Egyptosaurus. It attacks, bites, retreats, lets the prey bleed, tracks it, waits for it to weaken, then returns to feed. Pack hunting is possible. A group of Carcharodontosaurus could take down larger prey. Coordinated attacks, different individuals biting different parts of the body, overwhelming the defenses. But there's another large theropod, Bahariosaurus, less well known, similar size to Carcharodontosaurus, 8 to 12 meters, fragmentary fossils, but present. Maybe it occupied a different niche, different prey, or different hunting strategy. Coexistence of multiple large predators suggests abundant prey, high productivity. Lots of herbivores to support multiple carnivores. The herbivores, Uranosaurus, a hadrosaurid relative, 7 meters long, maybe 2 tons. Distinctive feature, a sail on its back, neural spines elongated, supporting a skin membrane, possibly, or a fatty hump, like a bison. What's it for? Thermoregulation, display, fat storage, all plausible. The sail increases surface area, could radiate heat, help cool the animal in hot environments, or absorb heat in the morning, warming up quickly. Display seems likely too. Males might have larger sails than females, used in mating displays or intimidation. Hump for fat storage works if food is seasonal. Store energy during the wet season. Use it during the dry season. We don't know, the fossils don't tell us, but it's there, a distinctive feature. Nigersaurus, a sauropod, 9 meters long, 4 tons. Small for a sauropod, but specialized. The skull is bizarre. Wide, flat, the snout is squared off, and the teeth, over 500 teeth, in rows, packed together, replaced constantly, every 14 days, faster than any other dinosaur. The teeth are aligned in a straight edge at the front of the mouth, like a lawnmower blade or a vacuum cleaner. Nigersaurus fed on ground-level vegetation, swept its head side to side. Cropping plants, ferns, low shrubs. The neck is short, can't lift the head high, doesn't need to. It's a specialized ground feeder, niche partitioning. Different sauropods feeding at different heights, reduces competition, allows coexistence. Rugops, a smaller theropod, maybe 5 meters long, half a ton. Abelisaurid, scavenger possibly. The skull shows evidence of rugose, wrinkled bone on the snout, maybe supported a keratinous horn, or thickened skin, used in display, headbutting, social interactions. Rugops is less common than the big predators, but it's there, filling a niche, opportunistic, eating whatever it can find, carcasses, small prey, eggs, pterosaurs, alanka, ajdakid, 4-meter wingspan. Terrestrial stalker, long neck, long beak, walked on the ground, hunted small animals, lizards, early snakes, mammals, crocodile hatchlings, anything small enough to swallow, and fish-eating pterosaurs, ornithochirids, coastal, soaring over the ocean, dipping to the surface, snatching fish. The diversity is high, multiple species, different niches, coexisting. The environment is dynamic, seasonal flooding. The rivers overflow during the wet season, create vast deltas, swamps. Dinosaurs move to higher ground, or adapt. Some species are semi-aquatic by necessity. The dry season, water retreats. Pools remain, isolated. Waterholes become focal points. Herbivores congregate. Predators follow. Ambush sites. Carcasses accumulate. Scavengers thrive. It's a cycle. Repeated annually. The ecosystem is adapted to it. Boom and bust. Feast and famine. And then there's the Tethys Ocean, the great east-west oceans separating northern and southern continents. Warm, shallow in places, deep in others. Full of life, ammonites, nautiloids, bony fish, sharks, marine reptiles. Mosasaurs are present but not yet dominant. This is mid-Cretaceous. Mosasaurs are just diversifying. Plesiosaurs still hold many niches, but the transition is happening. By late Cretaceous, mosasaurs will rule. But here, in North Africa 100 million years ago, it's a mixed community. Competition, predation. The ocean is productive, supports a complex food web, and the coastal zones where freshwater meets saltwater are especially rich. Estuaries, nurseries for fish, hunting grounds for reptiles, Spinosaurus territory. The Chem-Chem fauna is unique. High diversity of large predators, Spinosaurus, Carcharodontosaurus, Bahariosaurus, Sarcosuchus, multiple large carnivores coexisting. This suggests high productivity, abundant prey, but it also suggests niche partitioning. Each predator specializes. Different prey, different hunting methods, different habitats. Spinosaurus in water, Carcharodontosaurus on land. Sarcosuchus ambushing at water's edge. Minimal overlap, minimal competition, coexistence through specialization. Now let's go east. Asia, specifically the Gobi Desert, Mongolia. Today it's arid, sand, rock, extreme temperatures. But in the late Cretaceous, 75 to 70 million years ago, it's different. Still arid, but not lifeless. Seasonal rains, ephemeral lakes, oases, vegetation clusters around water sources, and dinosaurs. Lots of dinosaurs. Protoceratops, small ceratopsian, 2 meters long, maybe 200 kilograms. No horns, just a small frill, but common, very common. We find hundreds of fossils, bone beds, nesting grounds. Protoceratops laid eggs in nests, colonial nesting, groups of females nesting together. The eggs are elongated, oval, laid in circular patterns, buried in sand, incubated by solar heat and environmental heat. The adults might have guarded the nests, or not. Evidence is ambiguous. But the eggs are there, some with embryos, fossilized in place. Velociraptor, the famous one, but not the movie version. Real Velociraptor is small, 2 meters long, 15 kilograms, turkey-sized, covered in feathers. We know this from related species. Microraptor, Genuanlong, similar animals with preserved feathers. Velociraptor probably looked similar. Feathered body, long feathered tail, arms with long feathers forming wing-like structures, not capable of powered flight, but maybe gliding or display. The sickle claw on each foot, 8 centimeters long, curved, sharp, retractable, used for gripping prey, climbing onto larger animals, slashing. Velociraptor hunted in packs. Probably, a famous fossil shows a velociraptor and protoceratops locked in combat. The raptor's claw in the ceratopsian's throat. The ceratopsian's beak clamped on the raptor's arm. They died fighting, buried rapidly. Flash flood or collapsing sand dune. Preserved forever. The fighting dinosaurs fossil. It's extraordinary. A snapshot of predation, frozen in time. But Velociraptor didn't always win. Protoceratops had a powerful beak, could bite, hard, and there were other predators, larger ones. Tarbosaurus, Asian tyrannosaur, 10 meters long, 5 tons, similar to T-Rex, close relative. Tarbosaurus is the apex predator of the Gobi. Hunts hadrosaurs, sauropods, anything large. The bite force is immense, bone-crushing. We find prey bones with Tarbosaurus bite marks, characteristic punctures, V-shaped in cross-section, matching the tooth shape, Therizinosaurus. Now here's something bizarre. A theropod, but not a carnivore. Herbivore, 10 meters long, 5 tons, bipedal, with the longest claws of any animal. The hand claws are 1 meter long, curved, but not for killing, for pulling branches, stripping leaves. Therizinosaurus is a herbivorous theropod. It evolved from carnivorous ancestors, but switched diets. The beak is toothless or has small leaf-shaped teeth used for cropping vegetation. The gut is enlarged, fermentation chamber, like sauropods, but in a theropod body plan. It's convergent evolution, different lineage, same solution. Herbivory, large body size, slow metabolism. The rhizinosaurs are successful. Multiple species. Asia, North America. They're filling a niche. Oviraptor, another theropod, 2 meters long, 30 kilograms. The name means egg thief. It was found near a nest of eggs, assumed to be stealing them. But later, more nests were found, with Oviraptor skeletons on top, brooding, sitting on the eggs, like a bird, protecting them, incubating them. Oviraptor wasn't stealing eggs. It was guarding its own. The name is a misnomer, but it stuck. Oviraptor is an omnivore, eats plants, small animals, eggs, maybe, but not as a primary diet. The skull is short, deep, strong bite, cracking shells, nuts, mollusks. Versatile feeder. Gallimimus, ostrich mimic, 6 meters long, 400 kilograms. Fast runner, could reach 50 kilometers per hour. Toothless beak, omnivore, eats plants, insects. Small animals. Opportunistic. Gallimimus is common. Herds. Trackways show groups moving together. Safety in numbers. Predator avoidance through vigilance and speed. Pterosaurs. Large ajdarchids. Walking on the ground. Stalking. 4-meter wingspans. Smaller pterosaurs too, but declining in diversity. Birds are present. Small. Enantiornithines. Beginning to diversify, but not yet dominant. The environment is harsh. Water is scarce. Dinosaurs concentrate around oases, lakes, rivers. Competition for water is intense. Dry season, some water sources disappear. Animals die. Carcasses accumulate. Scavengers feed. Predators hunt the weak. The survivors move, migrate to areas with water, or go dormant. Some species might estivate, bury themselves, reduce metabolism, wait for the rains, like modern lungfish or desert frogs. We don't have direct evidence, but it's plausible. Sandstorms are common. Dunes shift, bury animals, sometimes alive. Rapid burial creates exceptional preservation. The Gobi has some of the best preserved dinosaur fossils in the world. Complete skeletons, articulated skin impressions, eggs, embryos, nests. It's a paleontological treasure trove because the environment killed and buried rapidly. Catastrophic for the animals, wonderful for science. Now Europe, late Cretaceous, 70 to 66 million years ago. Europe is not a continent. It's an archipelago, a chain of islands. The Tethys Ocean has flooded the region. Sea levels are high. Only the mountain ranges remain above water. The Alps are forming. Continental collision. Africa pushing into Europe. Slow, but the mountains are rising. And they create islands, isolated. Some large, some small. And on islands, evolution does something predictable. It makes things smaller. Island dwarfism. When a population is isolated on an island with limited resources, large body size becomes a disadvantage. Large animals need more food, more space. In a limited environment, selection favors smaller size. More efficient, lower resource requirements. Over generations, the population shrinks, dwarfs. We see this today. Pygmy elephants on islands in Indonesia, smaller than mainland elephants. Island foxes in California, smaller than mainland foxes. Komodo dragons, the largest lizards, but on an island, isolated. In late Cretaceous Europe, we find dwarf dinosaurs. Magyarosaurus, a titanosaur, but small, 6 meters long, maybe 1 ton, compared to mainland titanosaurs, 35 meters, 70 tons. Magyarosaurus is 1/10 the size. Same family, Different environment, island dwarfism, and dwarf hadrosaurs. Telmatosaurus, 5 meters long. Mainland hadrosaurs are 10 to 12 meters, half the size. Smaller prey, smaller predators. The whole ecosystem scales down. The predators are small too. Balor, a dromaeosaur, 2 meters long, but stocky, heavily built. Each foot has 2 sickle claws, not 1, 2. Unusual. Maybe an adaptation for island life. Different prey, different hunting strategies. Balor is the top predator on its island, but on the mainland it'd be mid-sized, vulnerable. On the island, it's king. Why does island dwarfism happen? Resource limitation is obvious, but there's more. Lack of predators. On the mainland, large herbivores are safer from predators. Size is defense. But on an island with no large predators, size isn't necessary. Selection for large size relaxes, and selection for efficiency increases. Smaller animals reproduce faster, reach maturity sooner. In a stable island environment with no major predators, small is advantageous. But islands are risky. Limited resources, vulnerable to environmental change. A drought, a volcanic eruption, a storm, the whole population can go extinct. No immigration from mainland, no genetic rescue. Islands are evolutionary dead ends, often. But they're also laboratories. Natural experiments in evolution. Europe's island dinosaurs show us evolution in action. Rapid size change. Adaptation to new conditions. In a few million years, a population can transform, shrink by half or more. The European islands are lush, despite being small. High rainfall, warm climate. Vegetation is dense. Angiosperms, conifers, ferns. The forests are thick, dark. Understory is limited. The canopy blocks light. But at the edges, where light penetrates, growth explodes. Clearings, riverbanks, coastlines. These are productive zones. Herbivores congregate. Predators follow. Marine reptiles patrol the waters between islands. Mosasaurs, plesiosaurs. They hunt fish, ammonites, each other. The islands are stepping stones. Occasionally, an animal swims from one island to another. Rare, but possible. Gene flow occurs. Slowly, populations on different islands diverge, become distinct species, but occasionally interbreed. When a storm blows an individual off course, or a log raft carries passengers. Accidental dispersal. It's how islands are colonized, and how diversity is maintained. Pterosaurs are important in the island ecosystem. They fly, ignore the water barriers, move between islands easily, carry seeds, nutrients, connect the islands ecologically. Seabirds do the same. Enantiornithines, fish eaters, they nest on the islands, bring marine nutrients inland. Guano, fertilizer, enriches the soil, supports plant growth. The islands are small but productive because of the marine connection. Europe's island fauna is unique and short-lived. By the end of the Cretaceous, sea levels begin to drop. The islands merge, reconnect. The island species go extinct, outcompeted by mainland species. Or they hybridize, blend back into mainland populations. The uniqueness is lost. But for a few million years, Europe is a natural laboratory, showing us evolution's flexibility, adaptation to isolation, and the fragility of island ecosystems. Let's talk about senses, colors, sounds, behaviors. What was it actually like to live in the Cretaceous? As a dinosaur or as an observer? If you could somehow step back into that world, what would you experience? Start with sound. The Cretaceous was loud. Hadrosaurs were the noisiest. Those crests, hollow structures on their heads. Parasaurolophus has a long, backward-pointing crest, 1.8 meters long. Inside, Nasal passages loop through the crest. When the animal exhales forcefully, air rushes through the passages, resonates, produces sound. Low frequency, infrasound, below the range of human hearing. But we'd feel it. A rumble, vibration in the chest, like standing next to a large speaker at a concert. The sound carries far, kilometers, through forests, across valleys, used for communication, identifying individuals, coordinating herd movements, attracting mates, warning of predators. Each species has a different crest shape, different call. Acoustic species recognition. You hear the call, you know what species it is, without seeing it. Corythosaurus has a helmet-shaped crest, different internal structure, different resonance, higher pitch than Parasaurolophus, still low frequency, but distinct. Lambeosaurus, another crest type, another call. The soundscape of a Cretaceous floodplain is layered. Multiple hadrosaur species, each calling, overlapping, a chorus, and it's constant. Dusk and dawn, peak calling times, like modern bird dawn chorus, but deeper, louder, felt as much as heard. Theropods vocalized too, probably. Modern birds are theropods. They vocalize complex songs, calls. Crocodilians, the closest living relatives of dinosaurs besides birds, vocalize, bellows, hisses, roars. So theropods likely did too. T-Rex, deep, resonant calls, low frequency, intimidating, territorial, males calling to females, or warning rivals. The sound might vibrate the ground, felt through the feet, a tyrannosaur approaching. You'd hear it, feel it, before seeing it. Smaller theropods, higher-pitched calls, chirps, clicks, dromaeosaurs coordinating pack hunts, short vocalizations, signals, attack. Retreat, surround, communication during predation, like wolves or lions. Social carnivores need vocal communication. It's efficient. Ceratopsians, bellowing, snorting, males challenging each other, posturing. If vocalizations don't settle the dispute, they fight. Horns clash, frills bang together, the sound of impact, bone on bone, echoes through the forest. Other animals hear it. Take note. A fight is happening. Stay clear. Sauropods, low-frequency rumbles. Infrasound again. Traveling long distances. Coordinating herd movements. Warning calls. A mother calling to offspring. The offspring responding. Auditory bond. In dense forests where visibility is limited, sound is crucial. You can't see far, but you can hear far. Infrasound travels through trees, through hills, miles, insects, buzzing, chirping, crickets, katydids, cicadas, the background noise, constant. At night, particularly, a symphony of insect calls, mating calls, territorial calls. The sound level is high, overwhelming if you're not used to it. But for Cretaceous animals, it's normal. The soundtrack of life. Birds, early birds, enantiornithines, chirping, whistling, short songs, not as complex as modern songbirds. Those evolved later, in the Cenozoic. But Cretaceous birds vocalize, dawn chorus, territorial calls, alarm calls, when a predator approaches, high-pitched, sharp. Other animals recognize the alarm, flee, or freeze. Interspecies communication through alarm calls. A small bird spots a theropod, calls. Hadrosaurs hear it, become alert. The predator loses the element of surprise. Alarm calls benefit everyone, except the predator. Pterosaurs, probably vocalized. Crocodilian-like calls, hisses, barks, used for social interactions, mating, territorial disputes. Quetzalcoatlus might have had deep, resonant calls, like a large bird, heron, crane, or like a crocodile. We don't know, but silence seems unlikely. Vocalizations are too useful. Now color, This is harder. Fossilized pigments are rare. But they exist. Melanosomes, tiny structures in feathers and skin that contain pigment. They preserve, rarely. But when they do, we can infer color. Microraptor, black, iridescent, like a crow. The melanosomes are shaped in a way that creates structural color. Interference, light waves interacting, producing blues, greens, shimmering. Display, attracting mates, intimidating rivals. Sinosauropteryx, striped tail, reddish brown and white, countershading, dark on top, light on the belly. This is camouflage. It counteracts the effect of sunlight. Sunlight makes the top of an animal brighter and the bottom darker. Shadows. Countershading reverses this. Makes the animal look flat, two-dimensional, harder to see, especially in dappled forest light. Sinosauropteryx was small, prey for larger theropods. Camouflage was survival. Psittacosaurus, countershading, dark back, light belly. Again, camouflage. Juveniles especially, small, vulnerable. Camouflage reduces predation. Adults might have been less camouflaged, larger, less vulnerable, maybe brighter colors. Display. But most dinosaurs didn't have melanosomes that preserve. So we guess. Based on modern animals, ecology, behavior. Large herbivores today are often drab. Grays, browns, greens, camouflage in vegetation, or just neutral. No need for bright colors. You're big. Everyone sees you anyway. But some use color for display. Zebras, stripes, okapi, stripes on the legs, social signals. Could hadrosaurs have had patterns? Stripes, spots, possibly. Males might have been brighter than females. Sexual dimorphism, attracting mates. The crests were for sound, but also visual display, maybe brightly colored. Reds, oranges, blues, like modern birds. Cassowaries have bright blue heads. Hornbills have colorful casques. Hadrosaur crests could have been similar. Ceratopsians, the frills, large, visible. Display structures, probably colorful. Patterns, each species different. Species recognition and individual recognition. Like faces in humans, you recognize individuals by their frill pattern. Coloration, horns might have been colored too. Keratinous sheaths, like horn sheaths in modern cattle. Bison could be dark, or light, or patterned. Theropods, feathered ones, probably colorful, like modern birds. Males especially, plumage displays, complex patterns, iridescence. Think peacocks, birds of paradise, pheasants. Males are flamboyant, females are drab. Sexual selection. Females choose mates based on appearance. Males compete. Display. The brightest, the most impressive, wins. Dromaeosaurs might have had colorful feathers, crests, tail fans, used in courtship or intimidation. Large theropods, T-Rex, probably less colorful, scaly, but maybe patterns, stripes, countershading, or uniform. Crocodiles are mostly uniform, gray, brown, green, ambush predators, camouflage. T-Rex might have been similar, or maybe juveniles were patterned, adults uniform. Ontogenetic color change, like some modern reptiles. Sauropods, probably drab, huge, camouflage pointless, neutral colors, grays, browns, maybe species-specific patterns, spots, stripes on the neck, visual signals. Recognizing your own species from a distance, or individual recognition. Social animals need that. Elephants recognize each other by appearance, sound, smell. Sauropods probably did too. The environment itself. Color. The Cretaceous flora was green. Like today, chlorophyll is green. Photosynthesis. But the flowers, angiosperms. Colors, reds, yellows, blues, purples. Attracting pollinators. Insect vision. Bees see ultraviolet. Flowers reflect UV, patterns invisible to us. but visible to pollinators. Cretaceous flowers did the same. UV patterns, guiding bees to nectar, co-evolution. The flowers are colourful. The forests are colourful. Not just green. Blooms. Seasonal. Wet season. Explosions of colour. Entire hillsides covered in flowers, attracting insects, which attract insectivorous dinosaurs, birds, pterosaurs, small theropods. The food web activated by flowering. Water, rivers, lakes, swamps, reflections. The sky, blue when it's clear, grey when clouded. The water mirrors it. Dinosaurs drinking. Their reflections. A hadrosaur herd at a riverbank. Dozens of animals. Ripples, splashing, movement. The scene is dynamic, alive. Behavior, social interactions. Hadrosaurs are social. Herds, dozens to hundreds of individuals, moving together, grazing, traveling. Safety in numbers. Predators target the weak, the young, the sick, the isolated. A healthy adult in the center of a herd is safe. Predators can't reach it. So hadrosaurs stay together, coordinate, follow leaders. Older females probably. Experience. Knowledge of migration routes, water sources, feeding grounds. Ceratopsians. Also social. Bone beds show mass deaths. Centrosaurus. Thousands of individuals died together, crossing a river during migration, flash flood, drowned. The bodies piled up, fossilized together. This shows they migrated in massive herds, like wildebeest or caribou, following seasonal rains, fresh vegetation. The migration is dangerous. Rivers to cross, predators. But staying put is worse. Starvation, so they move. Sauropods, less clear. Some bone beds, but fewer. Maybe they're less social, or their social structures are different. Loose aggregations, not tight herds. They're so large. Competition for food is intense. Spread out. Reduce competition, but they might gather at certain times. Breeding season. Water sources during drought. Temporary aggregations, then disperse. Theropods. Complex. Small theropods. Dromaeosaurs. Social. Pack hunters. Coordinated behavior. Hierarchy. Dominant individuals. Subordinates. Like wolves. Hunting together increases success, but also increases competition for food within the pack. Balance. Large theropods. T-Rex. Probably solitary, except during mating, or mothers with offspring. Juveniles might stay with the mother for a period, learning, then disperse. Establish their own territories. Adults are territorial, compete with each other, fighting, displaying, vocalizing. Winners get the best territories: food, mates, nesting, parental care. We have direct evidence. Maiasaura, good mother lizard, nesting colonies, dozens of nests, close together, colonial nesting, safety, predator confusion. If one nest is attacked, others are nearby. Alarm, defense. The nests are mounds, vegetation, dirt, eggs buried inside, incubation heat from decomposing plant matter, like crocodiles or megapode birds. The mother guards the nest, possibly brings food to hatchlings, crushed vegetation, regurgitated, feeding the babies. Parental care, rare in reptiles, common in birds. Maiasaura shows it existed in dinosaurs. Not all species, but some. Care increases survival. Offspring have better chances. Parental investment. Oviraptor, brooding, sitting on the nest. Body heat incubating eggs. The arms spread over the eggs, feathers covering them. Like a bird. The posture is identical. Oviraptor is more bird-like than reptile-like in behavior. Parental care, protecting the eggs. Maybe the male, maybe the female, maybe both. We don't know. But the behavior is there. Fighting, intraspecific combat, males fighting males, overmates, territory, resources, Pachycephalosaurus, headbutting, charging, Impact. The dome absorbs the force, distributes it, prevents skull fracture. Usually, sometimes things go wrong. Healed fractures in fossils. But most of the time, the fight is ritualized. Push, shove, test strength. Loser backs down, avoids injury. Winner gets the mate or the territory. Natural selection favors winners, but also favors restraint. Killing your rival is risky. You might get injured too. Better to display, intimidate. If that doesn't work, fight, but non-lethally. Usually, ceratopsians, horn locking. Males face off, lower their heads, horns forward, charge, horns clash, lock, push. It's a test of strength, neck muscles, leg strength. Who can push harder? The loser is pushed back, forced to retreat. The winner claims the female or the territory. Scars on frills and horns show this happened. Gouges, broken tips, healed injuries. Fighting was common. Part of life. Theropods, biting, clawing, more dangerous. Teeth and claws are weapons, used on prey, but also on rivals. T-Rex bite marks on other T-Rex bones. Healed. They fought and survived, but some didn't. Fatal injuries, broken jaws, infections. Intraspecific combat is risky, but necessary. Reproductive success depends on it. Males must compete. Winners reproduce. Losers don't, or reproduce less. Sexual selection drives behavior, morphology. Over generations, traits that improve fighting success increase. Larger size, stronger jaws, bigger horns, display. That's what much of dinosaur behavior comes down to. Sexual selection, competition for mates. Traits evolve not because they help survival, but because they help reproduction. A peacock's tail is a hindrance, heavy, conspicuous, makes you vulnerable to predators. But peahens prefer males with large, colorful tails. So the trait persists. Sexual selection. The same principle operates in dinosaurs. Ceratopsian frills, hadrosaur crests, pachycephalosaur domes, theropod feathers, all display structures. Males compete, females choose, or sometimes both compete, and the winners reproduce, passing their traits to the next generation. Intelligence. Let's address that. Were dinosaurs smart? Compared to what? Modern birds are intelligent. Ravens solve multi-step puzzles. Crows use tools. Parrots mimic speech, understand concepts. Birds are theropods, dinosaurs. So at least some dinosaurs were intelligent. But what about non-avian dinosaurs? The big ones. Sauropods, hadrosaurs, tyrannosaurs. Brain size matters. But it's not absolute brain size. It's brain to body mass ratio. Encephalization quotient, EQ. Humans have an EQ around 7. Dolphins, 4 to 5. Chimps, 2 to 3. Dogs, 1. Most mammals range from 0.5 to 2. Birds, 0.5 to 2 as well. Reptiles, 0.1 to 0.5. Lower. Dinosaurs fall somewhere in between, mostly on the lower end, but some higher. Troodon, a small theropod, 2 meters long, 50 kilograms. EQ estimated around 0.4. That's low by mammal standards, but high for reptiles, and comparable to some birds. Troodon had large eyes, binocular vision, depth perception, large olfactory bulbs, good sense of smell, and a relatively large brain. It was probably the smartest non-avian dinosaur. Could it use tools? Probably not. But problem solving, learning, social coordination? Likely. Pack hunting requires communication, coordination, theory of mind, understanding what others know, basic levels of that. Larger dinosaurs had smaller EQs, sauropods, 0.1, maybe less. They didn't need to be smart. Their survival strategy was size, eating constantly, reproducing. Intelligence is metabolically expensive. Brains consume energy. 20% of human caloric intake goes to the brain. For a 70-ton sauropod, supporting a large brain would be costly and unnecessary. They thrived for over 100 million years with small brains. Success doesn't require intelligence. It requires adaptation to the environment. And sauropods were adapted. Theropods were smarter on average. EQs around 0.2 to 0.4, depending on the species. Tyrannosaurs, 0.2 to 0.3. Not brilliant, but functional. Good sensory systems. Vision, smell, hearing. Capable of learning. Recognizing individuals. Maybe basic social structures. Juveniles staying with adults. Learning hunting techniques. Then dispersing. It's speculation, but plausible. The question of dinosaur intelligence brings up a thought experiment. If the Chicxulub impact hadn't occurred, would dinosaurs have evolved higher intelligence? Could there have been a tool-using dinosaur? A dinosauroid? This idea was proposed by paleontologist Dale Russell in the 1980s. A thought experiment. What if Troodon had continued evolving for another 66 million years? Could it have developed human-level intelligence? Russell's model showed a bipedal, large-brained dinosauroid, humanoid in proportion, forward-facing eyes, grasping hands, speculative, fun, but probably wrong. Intelligence evolves under specific pressures: social complexity, tool use, language. These require particular ecological niches. Humans evolved intelligence partly due to social competition, living in groups, competing and cooperating simultaneously. That drives cognitive evolution. Dinosaurs were diverse. Some were social. But the ecological context was different. Mammal intelligence evolved in the Cenozoic, after the dinosaurs, in a world where mammals filled many niches: small, nocturnal, diverse, competition, predation, pressure. Would dinosaurs have faced similar pressures? Maybe, maybe not. Evolution isn't predictable. It's contingent, path-dependent. Intelligence might have evolved, or it might not. We'll never know. Because 66 million years ago, an asteroid hit, and everything changed. The end of the Cretaceous. 66 million years ago, the world we've been describing, lush, diverse, dominated by dinosaurs. It all ends, abruptly. The Chicxulub impact, a 10-kilometer asteroid, traveling at 20 kilometers per second, hitting the Yucatan Peninsula in what is now Mexico. Shallow ocean. The energy release is 100 million megatons, not as large as Vredefort, but large enough. The immediate effects are catastrophic. Fireball, shockwave, tsunamis, global. Ejector ejected into space, falls back, heats the atmosphere, ignites wildfires across continents. The sky glows, everything flammable burns, and then the dust. Sulfur aerosols from vaporized rock. The Yucatan has gypsum, calcium sulfate. When vaporized, it releases sulfur dioxide. Sulfur dioxide in the stratosphere forms sulfate aerosols. Reflects sunlight. Block it. The planet cools. Rapidly. Impact winter. Darkness. Temperatures plummet. Photosynthesis stops. Plants die. Herbivores starve. Carnivores starve. The food web collapses. 75% of species go extinct, including all non-avian dinosaurs. Pterosaurs, mosasaurs, plesiosaurs, ammonites, gone. In geological terms, instantly. But some things survive. Birds, small, adaptable, omnivorous, seed eaters. Seeds survive in the soil, wait for conditions to improve. Birds eat seeds, survive. Mammals, small, nocturnal, burrowers, hide underground, eat insects, roots, whatever. Survive. Crocodilians. Aquatic. Can go months without food. Survive. Turtles. Similar. Lizards. Snakes. Some. Survive. Fish. Many species survive. Sharks. Rays. The survivors are small. Generalist. Adaptable. The specialists die. The large die. The complex ecosystems collapse. But some species make it through. And then, slowly, recovery. The dust settles. Sunlight returns. Plants recolonize. Ferns first. Fern spores are resilient. Spread quickly. The fern spike in the fossil record. A layer where fern spores dominate. Then angiosperms return. Trees. Forests regrow. Herbivores return. Mammals. Birds diversify. Fill niches. The Paleocene. First epoch of the Cenozoic. The age of mammals begins. Dinosaurs are gone. Except for birds. Mammals radiate, diversify. Within 10 million years, large mammals appear. 50 million years, whales, horses, bats, primates. The world transforms into the world we know. But imagine the alternative. No impact. The Cretaceous continues. Dinosaurs continue, dominating for another 66 million years to the present. What would Earth look like? Would dinosaurs still be the dominant land animals? Probably. They were successful, diverse, adaptable. No reason to think they'd decline. Mammals would remain small, nocturnal, marginal. Humans wouldn't exist. Primates wouldn't exist. Our evolutionary lineage depends on the extinction of dinosaurs, on the opening of ecological niches, on the opportunity for mammals to diversify. So we owe our existence to an asteroid, to contingency, to luck. The Cretaceous wasn't dinosaur decline. It was their apex, peak diversity, peak ecological dominance. They were thriving, and then, in a day, it ended. Not because they were unfit, not because they were failing, because a rock from space happened to hit at the wrong time, in the wrong place. 75% of species gone. The remaining 25% rebuild, slowly. And the result is the world we live in. A world where mammals, not reptiles, dominate. Where intelligence evolved in primates. Where humans build cities, write books, make videos. But it didn't have to be this way. The Cretaceous shows us an alternative. A world where reptiles, not mammals, are the architects of ecosystems. Where dinosaurs rule land, sea and sky for 165 million years. Longer than mammals have ruled since. The Cenozoic, our age, is only 66 million years old. The age of dinosaurs lasted 165 million years, more than twice as long. They were the most successful large animals in Earth's history, by duration, by diversity, by ecological dominance. And they ended not with a whimper, but with a bang. Literally, an asteroid, 10 kilometers wide, traveling at cosmic speed, obliterating the most successful dynasty the planet has ever seen. The Cretaceous ended in fire, darkness, extinction. But for 80 million years before that, it was paradise. For dinosaurs, a hothouse Earth, high oxygen, high carbon dioxide, warm poles, lush vegetation, flowering plants everywhere, dinosaurs everywhere, filling every niche, from tiny insectivores to 70-ton giants, from pack-hunting raptors to solitary tyrannosaurs, from ground-dwelling herbivores to tree-climbing omnivores. Diversity, complexity, success. The Cretaceous was the culmination of the Mesozoic, the third period, after the Triassic and Jurassic, and the longest, 79 million years, from 145 to 66 million years ago, named for the Latin word for chalk, Creta, because of the extensive chalk deposits formed during this time. The white cliffs of Dover, Cretaceous, formed from the shells of countless marine microorganisms, coccolithophores, plankton, their calcium carbonate shells accumulating on the seafloor, compressing into chalk, thick layers, across Europe, North America, elsewhere. The Cretaceous ocean was productive, full of life, plankton, fish, marine reptiles, ammonites, a complex marine ecosystem supporting the food web, from microscopic plankton to 15-meter mosasaurs. On land, the angiosperm revolution. Flowers, fruits, seeds, new plant strategies, co-evolution with insects, bees, butterflies, ants, pollination, seed dispersal, mutualism. The land becomes more productive, more diverse, supports more herbivores, which support more carnivores. The ecosystem becomes more complex, more interconnected, more resilient, until the asteroid. The Cretaceous was Earth at its most biological, most productive, most diverse. The climate was optimal, warm, wet, stable. No ice to disrupt, no glacial cycles, just steady warmth, steady productivity. For tens of millions of years, dinosaurs adapted, specialized, diversified, each region developing its own fauna. North America, South America, Asia, Europe, Africa, Gondwana, Laurasia, each unique but connected. Gene flow, migration, species spreading, evolving, diverging. The Cretaceous was a biological laboratory, evolution in action, on a global scale, for 80 million years, and we can see it in the fossils, Hell Creek, Gobi, Patagonia, Europe. Each tells a story, a snapshot, a moment in deep time, preserved, waiting for us to find, to study, to understand. Paleontology is time travel, through rocks, through bones. We can't visit the Cretaceous, but we can reconstruct it, piece by piece, fossil by fossil, study by study. And slowly the picture comes into focus. What it looked like, what it sounded like, what it felt like to live in a world ruled by dinosaurs. The colors, the sounds, the behaviors, the ecosystems, the climate, the continents, all different from today, but reconstructible, knowable, through science, through evidence, through careful analysis. And what we find is remarkable. A world more alien than we imagined, but also more familiar, because the principles are the same. Evolution, ecology, physics, biology. The rules don't change, the players do. But the game is the same. Survival, reproduction, competition, cooperation, predation, herbivory, the web of life. In the Cretaceous, in the Cenozoic, in any era. The same fundamental processes, driving diversity, complexity, the biosphere. And the Cretaceous biosphere was magnificent. The largest land animals ever, the largest flying animals ever, complex marine ecosystems, diverse terrestrial ecosystems, high productivity, high diversity, a world full of life, thriving, adapting, evolving, for 80 million years, stable, successful, the peak of the Mesozoic, the age when dinosaurs reached their zenith, their golden age, and then it ended, 66 million years ago. An asteroid, and darkness, and extinction. But the legacy remains, in the fossils, in the rocks, in the descendants, birds, the modern dinosaurs, flying, singing, thriving, carrying the lineage forward, from the Triassic, through the Jurassic, through the Cretaceous, through the extinction, into the Cenozoic, to today. Dinosaurs didn't go extinct, not completely. They evolved, adapted, survived, as birds, 10,000 species, more bird species than mammal species. The dinosaurs are still here, just smaller, and with feathers and beaks, but still dinosaurs, still theropods, still carrying the genetic legacy of the Cretaceous and beyond. When you see a crow, a sparrow, a hummingbird, You're seeing a dinosaur, a living connection to the Mesozoic, to the Cretaceous, to the age when their ancestors ruled the planet, when T-Rex walked Hell Creek, when Triceratops grazed in herds, when Quetzalcoatlus soared on 10-meter wings, when Argentinosaurus shook the ground with every step. That world is gone, but the lineage survives. In every bird, in every feather, in every song. The dinosaurs are not extinct. They're everywhere, flying, building nests, raising young, thriving, in cities, forests, deserts, oceans, everywhere. The most successful group of land vertebrates on the planet. Today, and for the past 66 million years. So when we talk about the Cretaceous, about dinosaurs, about the Mesozoic, we're not talking about ancient history disconnected from the present. We're talking about the roots of the modern world, the evolutionary context that led to birds, to mammals, to us. The Cretaceous ended in catastrophe, but it also created opportunity for mammals, for birds, for new life forms to evolve, to fill the empty niches, to rebuild the ecosystems, and create the world we know. A world where we can look back, through fossils, through geology, through science, and see what came before, and understand that Earth's history is dynamic, constantly changing. Continents move, climates shift, species evolve, extinction happens, recovery happens, life persists, adapts, survives. The Cretaceous teaches us that, shows us a world fundamentally different from ours, but also recognizable, because the processes are the same. The physics, the chemistry, the biology. Earth is Earth, whether it's hothouse or icehouse, whether it's ruled by dinosaurs or mammals. The planet persists, life persists, and we, today, are part of that continuum, part of the history, part of the ongoing story, a story that began 4 billion years ago with the first cells and continues today with us, with birds, with all life. The Cretaceous is one chapter, a long chapter, 80 million years, but just one chapter in a story that's still being written. Thank you for watching. If this journey through the Cretaceous has changed how you see the past, please consider subscribing. Understanding deep time, the vastness of Earth's history, the contingency of our own existence, these perspectives matter. The Cretaceous wasn't a prelude to our world. It was a complete world in itself, successful, thriving, until it ended, and something new began. That's the pattern. That's the history. Change, adaptation, survival. Until next time, remember, the world you see today is not permanent. It's a snapshot, one moment in deep time, just like the Cretaceous was. And like the Cretaceous, it will end, and something new will follow. That's Earth. That's life. That's time.